Hello, everybody, and thank you so much for joining me tonight. Today, we're going to be talking about chapter 4. It is all about character code. The reason why this chapter is important because it gives you an idea. Because we've been talking about numbers and converting numbers between decimal and binary, but what about characters? If I wanted to write something, the word code, for example, how am I going to write this C? Because it's a letter, it's not a number. So there was a need to have a certain understanding or an agreement in the scientific community to decide how are we going to represent the letter C. And then they found some problems and then they decided to change the standard and so on. We're going to talk about all that in this chapter. So the learning objectives in this chapter will be to gain familiarity with the ASCII code generally, and that's a character representation, and that's actually standard. That's an American standard. Understand the meaning of character and string comparisons, master the character and string operations, and understand the Unicode character representation. Unicode is the next level from ASCII. Okay, we had some issues with ASCII because it was limited, 7 bits only. Then we decided, you know what, how about we go to 8 bits or maybe 16 or maybe 32 because we wanted to represent other languages, for example, because ASCII is only mainly English. Now, some definitions we wanted to make sure we introduce them as you see in your book. So the ASCII standard, that's actually, it stands for American Standard Code for Information Interchange. So as you see, it's information interchange. Basically, there is a sender and a receiver. There is a typer and a reader, something like that. So there must be a way for us to represent all the characters that we use and we type. So that's where the American Standard Code for Information Exchange was created. It is based on 7 binary bits of a character, but it only covers English writing systems, and that's in itself is a big limitation. Unicode, an information technology standard, again, that's another standard for the consistent encoding, representation, and handling of text expressed in most of the world's writing systems. As you may know, not all languages write in Latin letters, like A, B, C, and all that. And the characters they use are completely different from Latin. Arabic, Chinese, Japanese, all those, they have different characters. So we found ourselves needing some kind of a Unicode, basically, a unified code that all languages can use and everybody can use so they can type letters, for example, or they can write stuff in the computer other than English. And we wanted to also mention the non-printable characters. As you may know, ASCII has 33 characters that are controlling purposes. They are non-printable, and the other characters, total of 95, which is generally between the two is 128, and that's 2 to the power of 7. Okay, so 7 bits will allow you, if you have 7 bits, the combination of 7 bits, you can end up with 128 characters in binary, and those 128 characters, 33 of them are non-printable and 95 are. What's in those 95? We will talk about it in a minute. So why it matters? Computers store text as numbers, so we wanted to find a way to store text as numbers. Why? Because we wanted to make sure we can convert these numbers into binary so we can store it, because the key word here is store. How does computer store data? Zeros and ones. So if we want something to be stored as zeros and ones, we need to have some kind of an agreement. How do we represent them? How do I represent A, for example, in zeros and ones? ASCII allows us to see that. Characters must be standardized. You cannot basically store an A here in the US in a certain format, and then the same letter can be, you want to store it somewhere else, let's say in England or France, in a different way. So it has to be unified This way, however it is written here in binary, it can be retrieved again in the other side of the world in binary when it's converted to decimal and then to a letter. It will give us the same letter, right? Enable communication between systems. That's the same thing, because if you don't have the right encoding scheme or the right encoding standard, you will not be able to retrieve the right data. So even if it is the same zeros and ones, when it's encoded or decoded, it will give us the wrong thing. So character code, as you see in this representation here, for example, the letter A, it's human readable. We know what A is. Computer does not know what A means. Okay, if you write an A for the computer, it doesn't know. If you take a picture of this letter right here and tell me what is this, of course, with AI, it will figure it out. But without AI, it wouldn't know what it is, unless if it knew that this letter represented with ASCII code is actually the number 65. And if you convert this into binary, it will give you this letter, this number. As you see, 1, 2, 3, 4, 5, 6, 7. But 8 became an ASCII code of 8 in, I believe, 96 or something like that. So that's when the last version of ASCII was created. Now, early character encoding. So as you see, this is basically where the idea came from, the telegraph codes, because we needed to have some codes to send these letters across the nation, basically, using these dashes and these dots. If you think about it, these dots are probably zeros and the dash is 1, or the opposite, ones and these are zeros. So only two ways of doing it when it comes to telegraph. So it's either a dot or a dash. And then those dots and those dashes, based on how many dots and how many dashes, does represent a certain letter. So they said, well, you know what? We can use the same thing and create it based on these two states, just like binary. We have also two states in binary, which is zeros and ones. We can use zeros and ones to represent every letter, every punctuation, and all that. And that's where ASCII was born. So we found that there is a problem with the hardware constraints. We needed to find a way to represent all this, and we wanted to have some kind of a conversion that will allow our hardware to retrieve whatever data we send in or whatever data we type in. Whenever we're trying to retrieve it, we need to make sure it's retrieved the proper way. If you store an A, when you retrieve it, it's still going to come up as an A, okay, in the same machine. But if you're using different machines, the one that's sending and one that's receiving, in the one sending is sending with a different encoding scheme than the one receiving. And if you send an A, the other side, it's not going to be the A. It's going to be something different. Once they convert the zeros and ones into using the receiver's encoding scheme, it will probably show a different letter or maybe a character of some other type. Now, this is an overview. As you see here, we talked about ASCII as its beginnings, which was 7-bit encoding. So 2 to the power 7, that's 128 possible characters. But wow, now we have 8. ASCII structure. So there's non-printable characters, as I said, 33, and printable characters will be 95. In this 95, you see the zeros are to 9, and you see A to Z lower cases and then upper cases, and some punctuation. And we're going to see in the next slide what are all the combinations into the ASCII table. This is it. This is the ASCII table. You can actually see, I remember a long time ago, we used to use this right here to create passwords that can be extremely hard to break. But it's the same thing nowadays. You can use these characters, okay, to create passwords. And it is extremely helpful. But for the moment, just look at these. As you see, The orders, we're going to talk about it in minutes, they specify there's 33 right here until here. They're basically not printable. So 0 to 32, which is 33 characters, will be unprintable. And right there, from this number right here, you can print them, because space is basically nothing, right? You just print a space. But it is also considered a non-printable character because it's not printing anything, it's just a space. Other than that, from 33 and up, they're all printable characters, 95 of them. And they include everything, but you do see that the letters, they don't represent anything. Like if you write in French, you have accents, like the E, it has an accent, and it's not in here. So then with that, you know what, ASCII does not answer all the requirement. It's not going to help people in other countries to use it. If we send them this and they have options for E, you know, there is different types of E's. I don't know if I can write directly on this. Probably can. Let me see if I can write directly on the screen. Okay, give me 2 seconds. So in French, for example, if you have this letter right here, you don't have it in English. You don't have this letter right here. Okay, these are letters in French. So we have things in other languages that we cannot represent here, even using Latin characters, because they have other things that can be added to them. And eraser. Okay. Now, that's basically an idea. How does the ASCII code looks like? If I tell you, write me an A in an ASCII code is 65. We're going to see an example in a minute. Then when you convert it into binary, it will be 8-digit binary. For example, these are basically A is a 65, base 10. Remember, ASCII code is talking about base 10. Okay, this is not binary. All these are base 10. These are hexadecimals. This is octadecimals, so on. And same thing for these characters. But as we mentioned here, these values, if we want to store them, and the key here is store them, because you need to put them as zeros and ones, you'll have basically to convert the 65 into zeros and ones, and that is what you store. So the character order, as I mentioned, as you saw in the charts, the upper comes before lower and all the punctuations before everything. And programming and characters. So in here, you probably have an idea what we mean by it. So for example, what is the ASCII code character 5? If we go back to the slide, 5, what is 5? Here is the number 5. It is 53 in decimal, right? So 53 in decimal, here it is. The other question is, in C or C++, what is the value V of the statement integer V? So remember this right here. It's saying it's an integer. V is an integer. Is 5, but it's considered the character here. Minus 0 is considered the character because of these symbols. But remember, there is a minus in between. So if it is considered the character, and this one is a character, it's basically telling us what is the binary number or the decimal number of 5, what is the decimal number of 0. You go to the ASCII code and you're going to find out 5 is a 53 and 0 is a 48. So you do 53 minus 48. It's 5 because V is an integer, so 5 is definitely just 5. Now, if V was a character, if it says char V, then number 5 will have to be represented as what's in the ASCII code, but it will have the symbols around it. Example 4, I didn't show you all the examples, but this one is cool because it's a Boolean, meaning the result will be just true or false. So in this option, the value B of the statement, Boolean B, is A superior to Z. So is A superior to Z? So you're gonna go to the charts, and you're gonna see what's the value for A, what's the value for Z, and you're gonna find out. So according to the ASCII table, the code for Z is 97, A and Z is 97 and 90. So A is 97, Z is 90, so A is superior of, Z. So this statement is true. So you're going to say B is true. That's basically what it is. Limitations of ASCII. So as we mentioned, it is only in English. So we needed to do something more. So it has no international symbols. So we can't represent words that are written in another language that doesn't use Latin characters. It's limited in size, only 8 bits, okay? Even with the extended ASCII. Extended ASCII is 2 to the power of 8, that's 256. Still not enough, because we know there is some characters in some languages that have thousands of letters. So we have to have a way to represent all those characters. Some limitations were adjusted based on vendors' preferences. So some vendors created different ways of doing things, okay? And they have the right to. They can convert as they see fit. They can build the hardware that can withstand those conversions, and they need to make sure their stuff is unified and can talk to the rest of the world. So as long as it can, if it's done internally, and a lot of organizations do that, they have hardware that internally talks in a different encoding scheme than externally. So they have the right to, so they can do that. Now, the Unicode, so why the Unicode was needed? So what's the Unicode basically? It's something larger than ASCII, something that will include all these letters that you see here. Okay, this example that I have here, it's just basically different languages, different letters, different representations. And if we don't have a way to represent them, these people will not be able to use the computers of today. So that's basically what it is. And then symbols and emojis. So we have a way now to represent symbols of emojis. That's what the Unicode is for. As you probably noticed, you can type in some characters one after the other, and it's going to change itself. I remember, I think when you do semicolon and you do like a parenthesis, comes up as a smiley face, something like that. So it's almost the same thing. So each one of those, you can find what code you can actually type in for these. And standardization issues. So because we needed to make sure that the ASCII, which was very limited, has a way to represent everything, and that's when we came up with Unicode. Unicode is generally what you hear about. That's the UTF-8, 16, 32, all those are Unicode. And each one of them is used for a certain reason. So it's the Unicode overview. So it's universal character sets, meaning it can be used by any language anywhere in the world. Supports many languages. What they mean here is many characters in many languages. I follow, by the way, the structure of the book to stay aligned with what the book has, but I always change things and add things, by the way. So backward compatible with ASCII, because Unicode has more letters than ASCII. But if you wanted to represent something was represented in ASCII and it wants to be read in Unicode, it will still be read because ASCII is basically included in Unicode. So all the codes that you have in Unicode already include ASCII. For example, if you look for the letter A, in ASCII, we know it's 65. In Unicode, it's still going to be 65. Unicode code points. That's basically how it's written generally. We're not going to go into details how it's written, but I just wanted to give you an idea. The abstract character numbers and not encoding specific. So it is unified and it's used by everybody. That's basically what it says there. So Unicode point, so Unicode expanded beyond 16 bits, starting with Unicode 2.0. That's in 96. Unicode 13, that's in 21, so it's the latest, not latest, there is more. Defines, this is the number of characters, 143,859. Remember, the other one was only 128 for ASCII. Now, this is how many characters we can represent with Unicode in 2021 across 154 written systems, including symbols and emojis. So when they say 154 written systems, I mean written languages, right? Unicode is a standard implemented using different UTF encodings. So UTF 8, 16, and 32. So 8 is the most used, and it's for web, Unix, and many other systems. And it's mainly used a lot because it's 8. So almost like the extended ASCII, which is also 8 bits, but the UTF-8 has more characters. It allows a lot more combinations. Therefore, it gives a lot of options, and of course, it allows us to represent a lot more. UTF-8 uses 1 byte for ASCII, so see, it includes ASCII, and up to 4 bytes for other Unicode characters. So it has a lot of space, and it allows more data to be represented. Here's an example of encoding. As you see, 32. This is how we're representing these characters. This is hexadecimal. So you see D, that's the polar hexadecimal. So in 16, that's how it will be represented. In 8, this is how it will be represented. 8 is right in between 16 and 32, as you see, character encoding. And 32 is the highest. And you see that when you have 32, UTF-32, for every characters, you need a lot of bits, a lot of bytes, meaning a lot of bits. So if you have to represent something with this many bytes, the data or the storage it's going to need is a lot larger, right? And if you're transmitting the data, it's going to need more time. So there is a drawback for UTF-32. Basically, right in between, you'll be dealing with UTF-8, and that's what's the most used. There's some characteristics for UTF-8 characteristics. So variable length, backward compatible, and most common encoding. Giving you an example here of UTF-8, how it's represented, the letter 2, 1, 2, 2. As you see, 2, when it's converted into binary, it's 0012. There's another 2, 0010, 0010, that's 2. And then 3 zeros and 1, that's number 1. And then 0010, it's another 2. So remaining bit to non-control bit of the first byte. So you can see these are the representation of the letter 2, and the remaining bits will be used for non-control. Next 6 bits to non-control bits of second byte, and then least significant bit to non-control bits of third bytes. You don't need to learn how to convert these letters like this, but it's just an idea so you can see the representation, that we go from a number or a character of some kind, and we end up with a binary number, and that's what's going to get stored. I wanted to show you something in here. So, for example, this is a representation of the trademark TM, these letters right here, TM. So this representation, by the way, if you want to type the TM trademark, you press Alt, and you type it at the same time 0153. Okay, Alt, hold it, 0153, you'll type the TM. So you may think, well, how did it happen? By typing this code, we ended up with this TM. It's because it's represented. It's in here, and the system knows exactly what you're talking about, because it is one character. This TM is actually one character. Now the UTF-16, 2 to 4 bytes. ETF16 shows up in the internal. And remember, in ETF8, it says 1 byte for ASCII and up to 4 bytes for the rest. So it's almost 5 bytes. And a byte is 2 bits. Actually, not 2 bits. 16. Okay, that's what it is. Byte is 8 bits. So 2 will be 16, 4 will be 32. Most famously Windows and Java, not because it's perfect, but because of a mix of history, compatibility, engineering trade-offs. So 16, it's mainly used a lot in the internals of many systems. UTF-32, generally, it's a fixed length. It's memory intensive because you need a lot of data, a lot of space, but it's simpler indexing because it's large, easier to find stuff. It's almost like you have an address, home address, for example, that's extremely specific. That means it will allow you to get to you. That's what indexing is, specifically allowing to find exactly what data you want. If it is, and of course it allows larger storage too. So here is a little bit of comparison between ASCII and Unicode. ASCII 7 bits when it started. That's how many characters it will allow. It's only in English. The Unicode have the option between 16, 24, 32, and between this many characters, and I want to read all this, and this many millions of characters depending on the system ASCII. So it contains all major languages, symbols, and hieroglyphs, etc. Extended ASCII is a character system where the first 128 characters are exactly the same as ASCII. So only the first 128, but because it has 8 bits, it allows more, so the rest will be controlled bits. Now, character code in memory, stored in binary values. Remember, computers only store zeros and ones, so it has to be binary. Encoding effect size, so more bits means more complexity, means needing more storage and more transmission. Same thing talking about transmission here. Larger data means longer transmissions. Real-world applications, as you may see in web pages, like this web page, you know what it is, and everything in the page is represented. If it's a letter, if it's anything, an address is basically letters, and everything gets at the end converted. Any code that you have within a page gets converted into binary at the end. Databases is the same thing. When you call in on a database, you're calling on a site where this information is sitting, and so on. Operating systems, every operating system has its own way of dealing with encoding. Okay. The common encoding issues, this one is called emoji bake. So emoji bake is basically when the data is not decoded properly. It's encoded with one encoding scheme and decoded with another, and if you do that, it does not. It shows like garbled, and it doesn't make any sense. But the computer is not showing the wrong data; it is interpreting the correct bytes using the wrong rules. So the agreement between the sender and the receiver, basically, the sender didn't tell the receiver, "Hey, I'm using UTF-8. You may need to use UTF-8 to open this stuff, because when it gets to the other side, it's going to be garbled." So in this example, basically, they're giving this, so this character will be shown instead of this character if you use in ASCII. ASCII, this character doesn't exist. If you use in Unicode, it exists and you can represent it. But in ASCII, it's going to come up something like this. Okay, so that's basically. So the common encoding issues, incorrect decoding occurs when a system applies the wrong decoding scheme to a sequence of bytes. Same thing we just said. Every encoding defines how bytes map to characters. If the decoder does not match the encoder, the resulting character will be incorrect and unreadable. and the bytes themselves are unchanged, only their interpretation is wrong. Big deal, okay? So common encoding issues, we're still talking about the issues. Encoding mismatch happen when different parts of a system assume different encoding. So let's say a system that's using internal encoding as UTF-16, and then it transmitting the data using UTF-8. So you may have some problems there, or the opposite, using ASCII internally and then using UTF-8 for transmission, you'll have an issue. For example, a file might be saved as UTF-8, but the application database or browser assumes it is ASCII or UTF-16 or smaller. This mismatch causes decoding errors and often lead to emoji bake. That's what the word is. If I ask you in a test what it means, you know exactly what it means by going through this. Common causes: file saved in one encoding and open in another web page, missing characters, or char set declarations. Basically, char set declaration is like you're not telling the system that it is a character or it is an integer or whatever. If there is a programming issue, it's gonna come up, show up wrong. Database and application using different default encoding. Big deal with databases. They're just like websites, but the information is retrieved, and it is extremely important to encode it properly or decode it properly. If you don't decode a database properly, all your information will be basically either unreadable, or if it is readable, you'll be retrieving the wrong information from the database, and that's a big deal. Imagine if you're storing credit cards, that would be a disaster. Encoding issues, that's a big picture now. Character encoding problems are not about broken data, they're about broken agreements. If the encoding and the decoding do not match, text will not display correctly, even though the binary data set is proper. And these are some best practices. Basically, if you have the option, always use UTF-8, be consistent, okay? UTF-8 all the way, and understand encoding assumptions. Sometimes, if you're seeing some problems, you know exactly what to say then. Okay, it seems like you have an encoding issue. And some of the problems, you can see it in some programs as well. You get an error, and you can see it saying that the encoding will say encoding, incorrect encoding, or something. Because I had this issue not long ago, actually, on a website trying to retrieve some reports. And in that report, you inject some selections, and you type them in. You actually type in the selections that you want, and it knows. But when you type in, sometimes you use some characters, and you're thinking maybe it's going to understand the characters I'm saying, the Boolean stuff, plus, add, or, and, these kind of things. You put them in there thinking maybe it's going to understand, but it comes up with an error message saying encoding scheme. And that's basically what it means. It means that it did not understand the command you're asking because it does not know where you typed, even if it is only one character wrong. Okay, this is the chapter summary. This was a very short chapter, so make sure you read it. It's simpler than chapter 3 we had last week. Okay, I know that chapter 3 did have some math in it and some symbols and things like that. I tried not to overwhelm you. I know some of you may be familiar with the math that it's in there, but in the future, if you tell me, if you feel like you're up for explanations that has advanced math like you saw in chapter 3, let me know. I'm a math guy, so my first degree was in mathematics, so yeah, I can explain those things and get you introduced to a little bit of a deeper explanation, dive a little bit deeper in the world of binary and what it means. And it is fascinating, I can tell you that. Okay. Now, thank you so much for your time and patience, and have a good evening. Bye-bye.